Researchers find an unfixable bug in every ARM CPU. I saw this. I really wanted to watch it, so I'm very stoked to be watching this. By the way, I don't know if you know this, but Ed, yes, his name is Ed, Low Level Learning, Ed, he will be on stream tomorrow to teach me all about ciphers, or Thursday.
Can computers see the future? Yes, sort of. In this video, we're talking about how the
Oh my gosh, I think I can already guess what's about to happen. I feel like I can already guess, dude. It's gonna come up with like that predictive branching memory reading nonsense. That's just crazy. It's just crazy stuff. I cannot believe that we have CPUs these days that try to we can't speed up a CPU pretty much anymore. So instead we have just the world's most complicated ability to try to predictively read and execute things. And the amount of bugs that have come from that is just crazy. The amount of security things that it's just wild.
The way that CPUs look into the future actually presented a memory corruption vulnerability that allows people to bypass a major feature of the ARM computer instruction set. This attack is one of those crazy ones, and I want to talk about this one so badly because any attack that uses a cache invalidation as a side channel to leak information about the CPU is already cool enough. Think about Spectre and Meltdown, right? Those bugs that broke the internet around 2016, 2017 time period. But on top,
I think Apple, right? Apple's the one that recently had this one where you were able to get the encryption keys for the Mac by doing, yeah, this is the O-face. This is almost a PogChamp right here. By just consistently doing this, you're loading, unloading, and then you're hitting it with some sort of XOR mask, and you're actually able to figure that out. Yeah, the Apple silicon. Yeah, it just cast the ARM, which is just, I cannot believe there's people that can perform that level of research. Like the amount of intimate knowledge you have to have where you are actually reading cache off the CPU to be able to try to hack into something. I don't know how many, does your basement have to be in your mother's basement? Like a double basement, like a Russian doll basement situation for you to have that level of knowledge? Like that is dude, intimate knowledge, dude. They're just going after wicked smat. Just wicked smat.
Top of it being a bug in a cache invalidation, it is also speculative execution. And via this attack, they're able to break one of the major pieces of ARM's security architecture. Now, if you're new here, hi, my name is Ed. This is Low Level Learning, a channel where I make videos about cybersecurity, software security, and all kinds of other cool stuff. So if you like that or just want to hang out, hit that sub button. I really appreciate it.
Already subscribed, losers. So I'll hit the like button instead. Losers.
Also, yes, I got a haircut. It's a little long, a little something weird going on here. Okay, I do want to give my hats off to the researchers here. All the people are named here in white. Please go take some time after this video, go read their paper. 18 pages of computer architecture goodness, binary exploitation goodness. In this video, I want to make this paper a little more digestible for people who may not have as much experience with how CPU memory works, how binary exploitation works, and all that kind of stuff. So what does...
I always have this problem where every time I see that there's a paper, I want to go read it and just spend an afternoon reading a paper. And then after I get done reading the paper, I realize I've spent an afternoon reading a paper and I haven't done anything else. And then I feel a little bit sad. One of us.
Memory tagging, what are buffer overflows, what is all this stuff about? Well, to understand how this attack works, we have to start at the basics. Hackers like to exploit these things called memory corruption vulnerabilities. The basic one that everyone knows about is a buffer overflow, right? This paper here by LF1 called Smashing the Stack from Front and Profit.
Anybody knows what LF1 is? Anybody? Quickly, go. LF1, infinity something. Let's go, Yuri. We got one person that gets it. It's the infinite set of whole numbers, right? Or is it LF0? Is LF0? I cannot remember if LF0 is the whole number infinity and then LF1 is real numbers infinity. It's bigger infinity, cardinality of infinity. Yeah. Great stuff. If you've never read on it, it's fun. Looking for the one soulmate. Nope, that's not what it is.
Which is a paper within FRAC, the hacker e-zine from a million years ago, talks about basically, hey, if we are able to write past the bounds of a buffer in C, we can use that to take control of the code by changing the return pointer. This guy LF1 enumerates that if we are able to control the return address of a program by setting this value to a hacker-controlled value, we can put code in that location and run malicious code. This has been the basis of the majority of the hacks that have happened, over 70% of them since the 1990s. And this is the thing that companies are trying to prevent by either secure code or secure architecture. Now,
I have never actually myself programmed in some sort of stack smashing, change the return address and make it do what I want, right? Like I've never actually tried to do that that it does sound like a fun little moment of life to see, like, can I get something to print hello world by going through, like, by altering the return address and doing my own world. It just seems fun. Do it, and then you'll be a hacker. Will I finally be a hacker? Do I have to live in my mom's basement? Or is this like the kind of hacker that's cool? Because right now, I'm not a hacker. I just ship bugs to production, okay? Mr. Robotogen. Yeah, I want to be that guy.
Now, ARM, the chip architecture designer that licenses out the ARM spec, has...
All hackers are cool. Are all hackers cool? I mean, because there was the furry hacktivist group that did leak lots of terabytes of data and own somebody because he tried to download a video game. Okay, so I'm not sure if all hackers are cool. Okay, I'm not sure if all hackers are cool. CSI hackers are cool. Yeah, agreed. Okay, agreed. Furry and hackers are opposite. Well, is it? Is that true? Not all hackers, but all hackers are furries. Is that how it goes? See, I know there's a rule. I know there's a Venn diagram that exists, but I just don't know which way the Venn diagram goes. Is it all hackers are furries, or all furries hackers? I can't tell.
Added several features in ARM v8 and ARM v9, one of them being this idea of memory tagging. So memory tagging is the idea of, just like it sounds, putting a tag or a specific number at the end of a pointer. By putting that number there, you effectively make a special number that if it gets changed, the CPU will crash. At runtime, the CPU checks that the pointer and the metadata tags on each load and store match. Now you're probably wondering, wait, aren't pointers memory addresses? Like, how are they able to just put a random value in a pointer? Well, pointers actually aren't all that magic. They actually have a specific function that they do. When you look at a 64-bit pointer, for example, there are a few things that are happening on the inside of this pointer, but basically almost the entire pointer is a series of indexes into tables. This index into table system is known what is called virtual memory that allows a program to think that it has access to all the memory on the CPU. By translating these virtual memory addresses to a physical memory address via page tables, we're able to give a program the illusion that it has access to the entire memory map. Meanwhile, it doesn't actually. It's a specific memory address that gets mapped into a pointer. Now, the entire pointer isn't...
Those are one of those things that, like, I understand in principle, but I have absolutely no clue how it works in practice. Like, I get the idea that look, I think this came around because, back in the day when you had a 32-bit architecture, you really only had access to 4 gigabytes of RAM, right? Because you couldn't have a pointer that was bigger than this thing. And so you kind of had to, like, pretend like you had this entire space fully available to you so you could do everything. And then when 64-bit came around, then you had access to all the units that you've ever needed in your entire lifetime. And so this has always been some sort of confusing world in which you don't actually, your addresses aren't actually addresses that go right into RAM, but they're addresses that exist in some sort of virtual translation space. And so I have no idea how this actually works in practice, but it always has seemed super cool that you have something that can be translated into another something that can be translated into another something that's actually your memory. Like, the idea seems really cool, but it seems like it's very, very confusing. Isn't it really a basic, like an array of addresses? Well, it's more than that. There's a translation layer that always seems a little bit confusing to me. I don't know a lot about that, right? It allows for memory protection. Before x86 programs could touch each other's memory. Yes, this is true. Memory protection is also very, very important, and we don't want to touch each other's memory, okay? We don't want to touch each other's memory together. That sounds dangerous. A little exciting, but mostly dangerous. Just took paging in university, and it's kind of complicated depending on the implementation. I could imagine that.
Actually used. There are certain bits that are reserved for special purposes or that don't actually do anything in the pointer. And so ARM has taken advantage of these leftover bits and used them to do specific memory protection elements, one of them being memory tagging. Another example is the pointer authentication code, where effectively the CPU will sign the pointer cryptographically, and if you overflow it, you invalidated the signature, and therefore the pointer is invalid. Also, real quick, this video is sponsored.
I would assume that has to be extremely costly as far as performance goes, or am I just crazy? Is this one of those things that there's like a special chip that just like does it all and it doesn't actually impact performance at all, or the overhead's very minor? But that sounds like I don't quite understand. This is where I wish I had more juice in my juice box here for this kind of stuff, which is just like how does having that thing exist? I guess I could see where if you overwrite, like, so for the return address, if you overwrite it with a different address, then its hash does not match to the return address. Therefore, it goes, hey, this is an invalid pointer. So I assume it's not done on userland pointers. It has everything to do with return address pointers or in pointers generated by some sort of compile time program. Am I correct on that? And thus, you don't get that. And I wonder how that juicing mentioned absolutely. And I assume that also. I assume there must be some level of access. It's done in userland pointers as well. Okay, interesting. It's all load and stores. Really, it's all load and stores. Is it because that when you overwrite, like, say, the return address, you can't properly overwrite it? But couldn't you just theoretically create a pointer and then you would have the signed pointer and then just take that tag and throw it in the return address? Like, could you just override that? Like, if you just had access like that, couldn't you just generate a pointer with the properly signed one and then just juicero that SOB right into the return address? Or am I just, again, smashing the stack for fun and profit? Tags are random. Well, you don't have access at that point. Okay, you don't have access at that point. Okay, yeah. It just, in my head, that seems like it's easily defeated versus, like, only having some. But again, you know, this is why I have you guys, is that some of you, there's at least one person in here that could help. I know I can't get LLL today. I'd get low-level learning in here today to kind of answer all these questions, but unfortunately, he has a dentist appointment today. So we're just kind of on our own, and he's not here to help us. Hardware magic, no visibility in userland. Okay, that's cool. That's super cool. Also, hello, Dylan Mulroy. Thank you for the raid. Hey, Dylan Mulroy. Hey, Dylan. Hey, yeah. Dylan. Casey could explain. I'm sure Casey could explain. I don't want to bother him to explain it. Could the dentist answer these questions? We could get the dentist in here. I think that'd be great.
Sponsored by none other than me. If you want to learn to code in assembly or C, or learn to do network code in C, please go check out my website, Low Level Academy. The courses are on sale.
I do actually want to see his networking code in C. I think that'd be a lot of fun. I actually am very, very curious if it's how he went about it and how good it is.
Right now for the summer, go check it out. If you
Do you think he does the full asynchronous sockets, reads and writes and everything, or do you think he just does just like a little bit here and there? Just a little bit. Like, his courses are great. I've never taken his courses. I've never looked through his courses, so they're great. Okay, that's good. You want to judge him, Prime? Lol. Yeah, I want to look at his networking code. I've done a lot of networking. I think it'd be fun. Non-blocking file descriptors, surely. Yeah. I mean, he's a smart fella.
In the C language, you could get a free preview with the arrays lesson here. If you want to go learn to code in assembly, you can get a free lesson with the load operations lesson right here. Please go check him out. I honestly believe that if you want to be a better programmer, you got to learn the fundamentals. Where do you learn the fundamentals? C
Agreed.
And assembly on Low Level Academy. Back to the video, memory tagging stuff. Memory tagging in ARM.
But he is correct, though. He is right. He is absolutely right. You should do stuff like that. You should learn the low level stuff. I like this though. I like this a lot. I like that. You should go check out his academy. I hear great things. I've heard so many people talk about how good it is. So I love low level. Yeah.
Also prevents against certain attacks like use after freeze, this place where you have data in a heap location, for example, you free it but accidentally access it later. The way it works is actually pretty cool, and this graphic here does a really good job of explaining it. So we have this character pointer here that gets allocated 16 bytes. When we allocate it with 16 bytes using an MTE compliant allocator, like the one on Android, for example, we can call this a particular color. Right now, the memory is blue. Now, what happens is we either can overflow this data or we can delete it. We can free it. And when we do that, we recolor the data to a different color. So this memory address now has a different tag. If we were to, in the future, use the old pointer, the use after free, but it still has that original tag, the blue color, this will throw a CPU exception. Now, the important part here is if the hacker is able to reveal the tag and put the tag back in place, this defeats the entire security of the system. The idea is that the memory tag, which is 16 bits, it hides in the first 16 bits of the pointer itself. If we are able to leak that tag, then this entire system falls apart. Now, this is where
Can you leak that tag? Can you not minus 16 bits from the pointer? Can you not do a little bit of pointer arithmetic and hop back one and grab it? Isn't this C-land? Isn't in C-land all you have to do is just cast that to a short and just walk back? You leak it so hard right now. Damn. People being crazy right now, chat. Did I also kind of understand that correctly, that now in C-land with ARM, they're having like very concrete because one thing I really like about, let me say it this way. One thing I really like about Zig is that when you do a use after free, when you do a double free, when you leak memory, it lets you know everything, where it leaked and everything. Is there some level of that happening now? Because this is pretty amazing that it could actually say like, hey, this thing, not only did you use the memory, you used the memory after it was free. You get that with address sanitizer? Okay.
Falls apart. Now, this is where the TikTag paper gets really, really interesting. Now,
By the way, that's where my few times using an address sanitizer is where I learned that I am a sloppy programmer in C. All right, that's what I learned. When I turn on that, when I do a little ASAN build and I look at it, I go, man, I'm terrible at this.
What they do is they use this thing called speculative execution. Now, we all want our computers to run as fast as possible, right? Ideally,
yeah, brother.
our computers would run our programs, it would load and store all of our memory, and it would never take what is called a cache miss, where effectively, when it looks up a memory address, if the memory isn't there in cache, it has to go out to random access memory and load that into cache.
Now, just to be clear, in C, you can... Isn't there something in C or C++ where you can actually like tag an if statement saying that this is likely the one that's going to be running, and it could potentially try to load that first? Isn't that like a thing you have, like some sort of branching optimizer, a hint, as they are called? Does that affect this thing? Branching hints? Yeah, intrinsic for branching hints. The likely tag or something. Yeah, there's like a likely tag. Is that an annotation for this thing? Attribute unlikely. Oh, it's unlikely. You go the other way. Great. Let's see. It was a compiler intrinsic before. Now C++ has attributes likely and unlikely. Okay.
Is very expensive. It causes the program to slow down. So there has been this push to do this thing called speculative execution, where your CPU will actually run the instructions that are ahead of the current program counter. It will go into the future and predict what path you're going to go down and try to preload that memory address to put it into cache so that when you actually get there, you don't miss the cache.
I can't believe there was a bug with that. Like, I'm personally shook that bugs happened because of that. I mean, you should be able to go into the future and execute things. This seems like a very bad idea. Well, the problem is that where this all, I mean, in my head, where this all comes from is that in the early 2000s to 2010s, we had huge amount of CPU wins. In the next 10 years, the CPU wins are just like not that great. And we're pretty much flatlined at this point. You're not getting much more at this point. It's literally a pre-watch bug. Like, CPU wins are just like not happening nearly as fast as they once were. And so you have to become ultra super duper clever. Everything that is happening on your computer needs to try to happen into the future. And so this is part of it, is that the speculative execution is where if you can just read in a straight line, it goes real fast. But if you have to hop all around, it's not fast. We still get like 15% almost every year. Yeah, but 15% is nothing like it was in 2000 to 2010. Remember in 2000 to 2010, like at 1999, I believe 450 to 600 megahertz was like the average range, if I'm not mistaken. By 2010, that shit was crazy high, right? It was like 2 gigahertz. Like it 4x'd over the course of 10 years. It was crazy. Dude, in 2000, we got 100% every 18 months. It was crazy. Yeah, those were the years. And then it stopped happening. We would be at like 12 gigawatts right now. Right? It would be absolutely amazing, but it's no longer happening that way. And so 460 times 4 equals 4,000. Let's go. Not even to mention core count. Yeah, and then core count and hyper threading and all the buzzwords that happened afterwards happened. Like, it was the golden era of compute increase was this time. Now we have to beat the final boss in a much more confusing way, right? We're at the official physics final boss, and this is much harder. And so this is where speculative execution really like plays a big role, is that it feels much faster if you can like execute in a nice straight line and have things preloaded, and it can go real fast. We're in the log X part.
Now, like I said in the beginning of the video, there have been a variety of memory corruption attacks or leaks that have come out of speculative execution, and spoiler alert, this is how the MTE leak works. Now I'm going to zoom in here to their graphic. I want to highlight this because this is really, really interesting. So the way that it works is they create a guess pointer and a test pointer that both live within the same 16-byte block so that they have the same memory tag. Now they create an area of speculative execution that will go out and try to dereference the guess pointer and dereference the test pointer. Now notice they don't actually ever go and run this code. All they do is they put it into the code in a way that it could conditionally execute. But the problem here is that if the tag mismatches, right, the whole point of memory tagging is that if the tag mismatches, it crashes a CPU. If it mismatches in a speculative case, if it mismatches in the future, it will not crash the CPU. And even so, if it mismatches, it won't cache. It won't go into cache. The test pointer will not be cache filled, and therefore the guess is wrong. So what they're able to do, they're able to time, did we already cache fill this test pointer, and use that to figure out if the tag that they guessed was correct. So what they do is they iterate, is tag 1 correct? Is tag 2 correct? And they keep checking over and over again until their access to test pointer is now filled in cache. Therefore, they're able to leak the tag of the target address.
I might have to read the paper, but how do you know that the cache was filled? I know this is like incredibly brilliant, by the way. Is it purely timing? Is it just literally just like you try to then read something and then you're able to say, oh, this was faster? Speed differences? Oh my gosh. Oh my gosh, that's so brilliant. It's so effing brilliant. Speed difference between trying to read. Priority queue. Priority queue. Dude. Priority queue for sure. This guy looks me, but with dedication, genius, good looks, and no girls. Actually, first off, he has a wife and a kid. Okay, tough guy. Okay, this man fully touches grass, touches ass, and touches pointers. Okay, wrecked. Get actually wrecked. Joke's on you, paid actor. Wow. Okay, for those that I think I generally understand. So there's the speculative case, right? That this code never actually gets ran. So you have this like test pointer, you have some sort of if conditioning or something like that might get ran. And so the speculative execution will go off and it will read this data. And if the tag is correct, since it's speculative execution, I assume that means it doesn't crash the CPU if it has a wrong tag. Since it doesn't actually execute, it only executes maybe in the future. It doesn't actually crash the program. So therefore, when the tag is wrong, it doesn't crash anything. Nothing is loaded into the, like, okay, we're good. It just speculatively executed. And then there must be some sort of way it can do some sort of timing here that we don't see. So there must be some sort of like, if it happens really fast, because I assume the tag crashing is like the first thing it checks. Checks the tag, can't do it, crashes. Therefore, this speculative execution must be super fast. Versus it should be much slower because it must be doing something in here that causes a bit of a slowdown. So I know you're probably measuring something like nanoseconds, but still, you at least have some sort of understanding like, hey, this was slow versus this was fast. But if it passes, then it knows it was able to load this speculative execution. Everything was great. And then it's able to know, okay, we've actually correctly guessed the tag. Now we can go here and now we can smash them stacks, baby. Let's do some return address overwriting. Felt cute, might execute later. Might execute. Oh my gosh. This is literally speculative execution in 5 words. This is what it is. If you don't understand speculative execution, maybe you understand it now. That's a t-shirt. That might be a t-shirt. Isn't this cool because it is hard to catch and easy to push faulty code? Well, it's cool in the sense that, to me, what's really amazing about this is somebody was smart enough to think of this. And I just like that. And I can kind of adopt all of that genius that they took in just a few minutes of going, oh, yeah. I still only understand it again. I've never actually done stack smashing myself. I mean, I've smashed some stacks. I'm somewhat of a stack smasher myself, but I've never actually done it myself in an intentional way. And so this is really amazing to be able to see someone's thinking, right?
And use that for a future memory corruption attack. Like when I read this paper, Not only are they doing cache side channel leaking, they are doing it in speculative execution to bypass a hardware memory protection. Dude, it is just one of the craziest bugs. And to make it even more crazy, what they figured out how to do is they're able to do this attack inside of the V8 sandbox. So what the entire structure here is they create
the V8 sandbox. Is he when he says V8 sandbox? Is he talking about JavaScript? Like as in Chrome Node? Like, because if you're able to do this in Node, that's crazy, yes? Yeah, like if you can unsandbox a sandbox, JS devs in shambles, actual shambles. Literally definition of hacker. Hackers repeat mistakes by intention, not by error. Yeah. Wow.
These things called TikTag gadgets. Now, this graphic that I just showed you is called a TikTag gadget template. So basically, if you can find a piece of code that does this sort of thing, where you have address you want to leak, address you control, speculative branch, and then you can check at the end of it, you've created what is called a gadget template. So if you can look for snippets of code that are like this, you can find ways to leak the MTE in other code. And these researchers actually found a bunch of TikTag leak gadgets in the V8 VM, which, as I've said in previous videos, is the V8.
That's super cool. I wonder, for those that haven't ever played with something called Tree Sitter, Tree Sitter effectively builds an AST for you, and it builds it at an incredible rate, right? Like you can go over an entire multi-million line code base in seconds, right? It's like, it's genuinely, it's absolutely amazing. And so the fact that they just created this TikTag gadget or whatever it's called, you could actually tree sitter the shit out of every single code base and find everywhere where it's at, and you could tree shitter it. Like, it'd be amazing.
VM that they use to run the JavaScript sandbox, right? And they're showing you here in this paper, and again, I'm not going to pretend like I know how all this works. It's very, very complicated, that they found TikTag V2 gadgets that can work inside the V8 sandbox to leak ARM V8 tags. So, like, I just cannot emphasize how crazy this paper is. I really, please go show them some love. Go read it. I hope I made this more accessible to you guys. And if you like this video, do me a favor, hit like it, subscribe, then go check out this video that you will also.
By the way, this is the challenge of every last weatherman ever existing right here.
If you like this video, do me a favor, hit like it, subscribe, then go check out this video that you will also like as well.
Let's go. Thank you for showing me my own video. That's fantastic, dude. That's so funny. That is so I even just got it backwards myself. It's this way for that one, this one for that one, dude. I do it all the time. And see, you can launder a pointer on the stack that contains an arena of your entire program. I allocated 50 megabytes on the stack up front and then laundered it using some ASM magic. Oh man, that's so magical. Like, I get all these things that you're saying in principle. It's just like doing it. It's the doing it part. It's quite amazing. I must say, it's quite amazing. Can you block your own channel from your Rex Prime? You know, I did not know that. One would assume that you should be able to not get recommended your own videos, for I created them. Just saying, it seems weird that I'm seeing my own thing. Like, not only am I familiar with the video, I said all of the things in the video. It just seems weird. Make your dreams come true. We're trying. The name is Low Level Learning is by far one of the smarter people on the YouTubes, okay? One of the smarter people on the YouTubes by far. Please go follow him. Go check him out. Shout out Low Level Learning. Please go. I know we already did an other shout out, so go click this. Go follow him. Go do all the things. The guy's great. The name is I'm a fan of Edigen, okay? I'm a fan.